We continue our introduction to problem-solving techniques for analyzing 1D constant acceleration motion in this second mini-lesson. In the first mini-lesson, we worked an example involving one object moving at constant acceleration between one initial event and one final event. These are the simplest, most straightforward constant acceleration problems. In this mini-lesson and the next, we'll consider richer, more complex examples. In general, there are two ways to add complexity to constant acceleration motion problems. First, the motion of one object might have two time intervals of interest, in which the final event of the first interval is the initial event of the second. The next type involves the separate motions of two objects that are related in some way as specified by conditions in the problem. This mini-lesson focuses on the first type, and the next one will focus on the second type. Let's do an example. A rocket sled starts at rest at the starting line of a long, straight test track. When the starting buzzer sounds, the rocket sled begins to speed up at constant acceleration. When it reaches a speed of v, it enters a muddy region which lasts for the rest of the track. The drag from the mud causes a 20% decrease in the sled's acceleration. It finishes its test run in a time t, crossing the finish line at a speed of 2v. Part A asks, what was the sled's acceleration before entering the muddy region? Part B, how long after the start of the test run did the sled enter the muddy region? Part C, how far from the starting line was it at this point? And Part D, how long is the test track? Our first job is to parse the situation described in the problem into events. Now, from the information provided in the problem and from the quantities we are asked to calculate, it's clear that there are three events. 1, the starting buzzer sounds. 2, the rocket sled enters the muddy region. And 3, the rocket sled crosses the finish line. That means there are two time intervals, or segments, of interest. Events 1 and 2 are the initial and final events, respectively, of the first segment, and events 2 and 3 are the initial and final events of the second segment. Our next job is to translate the problem into a sketch of what's going on. Here I show three snapshots of the motion arranged in parallel, each one depicting one of the three events. Even though I've drawn the clean and muddy stretches of the track to be the same length, that's just meant to be schematic. We don't know yet whether or not they're actually the same length, and I suspect they're not. With our sketch in hand, we're ready to construct a model in which we eliminate extraneous details and focus on the essential details. And once again, a particle model suits our purposes. In this picture, each dot, or particle, represents the rocket sled at one of the three events. Arrows indicate velocities, both direction and speed, and below each dot is listed the time, position, and velocity for each event, with unknown values indicated by question marks. The acceleration for each segment is listed between the corresponding events. I've chosen the origin of coordinates and time to be at the first event, and we're told that the sled is at rest at this event. All we know about the second event is that the sled has velocity v. We don't know the time or position of the second event. For the third event, we're given both the time, t, and the velocity, 2v, but we don't know the position. We aren't told the acceleration during either segment, but we do know that the acceleration during the second segment is 80% that of the first. So we're left with four unknowns: the acceleration during the first segment, the time and position of the second event, and the position of the third event. Not surprisingly, these four quantities are precisely what the four parts of the problem are asking us to determine. Let's write down the three constant acceleration equations for each of the two segments of the motion. Here they are for the first segment, with events 1 and 2 as the initial and final events, respectively. And here they are for the second segment, now with events 2 and 3 as the initial and final events. We can substitute in the values that we know, leaving the 6 equations in terms of only the 4 unknowns. Please note that for the purposes of this problem, v and t are to be treated as known even though they're represented by symbols rather than numbers. I like to think of them as quote-unquote given but unspecified. The value of using symbols rather than specific numbers is that this way you've actually solved a whole family of problems rather than just one specific instance of that family for particular values of v and t. Having 6 equations and only 4 unknowns means that 2 of the equations are extraneous. So let's focus on the upper 4 equations. Now we're ready to do some algebra to solve for the 4 unknowns in terms of the givens, v and t. We'll start with the equation that I've put a box around. And the first thing we do is cancel a v from both sides. We also multiply out the second term on the right-hand side. Notice that a combination a1 times t2 appears on the right-hand side. But we know from one of our other equations that a1 times t2 is equal to v. So we substitute that in. Next, we move the 4/5 v from the right side to the left and combine it with the v that's already there to give 9/5 v. Solving for a1 gives 9v over 4t. Now that we know a1, we can solve for t2. Since v is equal to a1 times t2, t2 is equal to v divided by a1. Substituting in for a1 and simplifying gives t2 equals 4/9 t. To find x2, we simply substitute our answers for a1 and t2 into the equation x2 equals 1/2 a1 times t2 squared. After simplifying, we find that x2 is equal to 2/9 times vt. Finally, we get x3 by substituting our answers for a1, t2, and x2 into the last remaining equation. After a little simplification, we find that x3 is equal to 19/18 times vt. Putting this all together, we can now answer all 4 parts of the original problem. The sled's acceleration before entering the muddy region is 9v over 4t. It entered the mud at a time 4/9 t after starting the test run, at which point it was a distance 2/9 times vt from the starting line, just over 1/5 the full length of the track, which is 19/18 times vt. As a check, it's worthwhile making sure that the dimensions work out for each answer. And indeed, v divided by t has units of acceleration, t has units of time, and vt has units of position. Here's a final question for you to ponder. What was the average velocity of the rocket sled over the entire course of its test run? It should be easy to determine this from the information on this screen, but if you're unsure, talk to one of your instructors or TAs.